Hey everybody, Dr. A here, and in this video we're going to be providing some background information on surface area loads, or sometimes just called surface loads. So basically these occur whenever you have a load that's spread out over a two-dimensional area. So let's go ahead and get started.
The last topic involving distributed loads that we're going to talk about are what we call surface loads. So these are loads spread out over an area surface. So instead of having loads spread out just over one line or one linear segment, it's going to be spread out over an area. So the units are force over area. So it's a lot like stress units, area of stress that are units of stress that we talked about in several videos ago in the past. So let's take a look at this. I'm going to draw a 3D surface here. Okay. So let's say that we have this 3D surface. Let's say it's like a plate, for example. Okay. And then let's say that we have this load that is spread out over this surface like so. All right. Now this load is meant to be spread out over this entire surface. So even though I'm really kind of emphasizing the perimeter of this load, really you can think of it as a load spread out over an entire surface. So another way I'm trying to draw it here is almost like a grid pattern where this load again it's spread out throughout this entire surface. And I'm going to call this Q, and I'm going to say Q is equal to force over area. Okay. Now, what is the area? Well, we're going to say that the area is this dimension B, and by this dimension L. So area is going to be LB. So really what we have is Q equals force over LB. Okay. So in a case like this, again, it's very similar to a load spread out over a length, except now it's just extended in 3 dimensions and it's spread out over an area. So the height of this distribution, right? We're going to say height of distribution is the intensity Q. All right. So that's it. So let's jump into a very quick example. We're only going to barely touch on this in this class, but let's look at the case of a uniform surface load. Okay, so a uniform surface load is the same idea as a uniform distributed load, except instead of over a line, it's over a surface. So here's what I'm going to say. I'm just going to jump right into an example of this, a very quick example. And we're going to say we want to compute the equivalent force due to the surface load. And we're just going to look at this, look at a simple rectangle. So let's say we have this rectangular area. Maybe it's a slab, or maybe it's a roof slab, who knows. And let's say that it's 8 feet by 10 feet long. And let's say that here is our surface load over this entire area. Okay, and let's say that the intensity is 100 pounds per square foot. Sometimes we call this 100 PSF. A PSF is the acronym for pounds per square foot. Okay, so we want the equivalent force due to this load. Well, if under solution, if if Q is equal to force over area, then we can say clearly force is equal to Q times area. So in this case, it's 100 pounds per square foot times 8 feet times 10 feet. And so we just have 100 times 80 is 8,000. So the force, the equivalent force is going to be 8,000 pounds. And we see that the units cancel, this 100 pounds per square foot. We see that the feet squared here cancel with each of these feet multiplied together, just leaving units of pounds. Now, my question, even though I didn't explicitly ask this in the example, where do you think this is located? Well, if you have a uniform distributed load, it's located right smack dab in the middle. So the equivalent system would look a lot like this. We have our area here, and then here's your F equals 8,000 pounds. This is not drawn to scale very nicely, but this is 4 feet and 4 feet. And then in this direction, it's located at 5 feet and 5 feet. Yep. And that would be the equivalent system due to that uniform distributed surface area load.